Okay, time to get started. Thank you all for coming to this special BIMR seminar. It gives me a great pleasure to introduce our speaker, Professor Naoki Komatsu from Kyoto University. Professor Komatsu did his honest education at Kyoto University. So he received his bachelor's degree in chemistry, right?
Yes.
In 1986, a master's degree in 1988, and his PhD in 1993. Again, all at Kyoto. And after he finished his PhD, he joined Okayama University as an assistant professor.
Yeah.
Where he stayed just 1 year, and then came right back to Kyoto University in 1994. Where he stayed up until 2003. And during that time, in 1997, he spent a year at Florida State University in the US as a sabbatical.
Yeah, 1 year.
Yes.
Yeah.
Then in 2003, he moved to the Shiga University of Medical Science as an associate professor, where he stayed until 2015. And then again, came back to Kyoto to be full professor at over his career, he has developed a really exciting research program that is generally referred to as sort of organic chemistry of nanomaterials. He has done a lot of really beautiful work on synthesis of supermolecular complexes, and has made many really important contributions to carbon nanotubes, fullerenes, various nanocarbons, nanodiamonds, and also some medicinal applications of many of these nanostructures. And today he's going to tell us a bit about lots of things, but mostly focused on separation of carbon nanotubes using post-test chemistry with this beautiful molecule.
Yeah. Thank you very much. Yeah. Kind introduction, and I'm very happy to be here. And actually, so that next slide, and I will introduce my long trip from Japan and go around the world. And so here, my trip started, so the May 11th, and from Kyoto to Beppu. Do you know where is Beppu? In Japan. This is Japan. And so you can see that this, right, and this image, and this is onsen in Japan, hot spring, and probably you may know that, very famous. So that Japan, right, and hot spring, and Beppu is one of the best, the hot spring, the place, and we can enjoy. And it's a sort of in the Kyushu Island. Do you know that, so that the shape of the Japan, right, and this kind of long island, and southern part of the island is so that the Kyushu Island, and the Beppu is located in one city in so the Kyushu Island, and I enjoy it. But actually, I joined the conference, New Diamond NDNC, New Diamond Nanocarbon Conference, international conference was held in Beppu, and so 400 participants were there, and I'm one of the organizers. That's why, so that I fully joined this conference from May 11th, and almost 5 days, 6 days, and then next, so from Kansai International Airport to Montreal through the Vancouver to join the Electrochemical Society meeting which was held in Montreal. This is the third time for me to join have been to the Montreal. But anyway, first time for me to visit this Fla Dome. This is the first time, and very impressive. And from the picture, I didn't know how big it is. But when I went there, and very big, right? And I was surprised and how big it is. But anyway, so this is a very good memories. And so at the end of this, so the conference, yesterday we moved with Alex, and from the Montreal to the Hamilton. And so tomorrow we will go, yeah, so in the evening, I will get on the flight, and from Toronto to this city. Do you know where it is? And you can guess which city? not Paris, but France. Probably not. No, no, Strasbourg. Yeah, this is Strasbourg, and where we met with Alex and last April, and so the Chem on Tube, that is also the international conference was held in the Strasbourg, and so we met each other at the conference. It's the chemistry related, so the conference, and yeah, of course, so every participant are interested in the carbon nanotube, but from the chemistry side, and yeah, that is a very fascinating. So the international conference. But anyway, so that tomorrow I will move from Toronto to the Strasbourg and go to Europe. And then, so that at the end of I will join the EMRS conference, European Material Research Conference. And yeah, MRS, yeah. And so they go to Strasbourg and stay almost 1 week, and then at the end of the stay in Strasbourg, and I will move to Berlin and to visit my friend at the Free University of Berlin, and I will have a talk and over there, King, and then May 31st, and I will leave Europe and to get to to come back to Japan on the June 1st, and it's a very long trip and go around the world, and it's a world tour for me. And okay, so let's start the research background for me. And so this x-axis stand for my research career. Actually, so my research career starts at the end of the 1980s, and so this y-axis is a logarithm of the molecule or the material I have been working with, and so I'm an organic chemist. I got a PhD, so to do the research about the organic chemistry, and at that time, so I was working with the molecule, which has a molecular weight of the few hundred or the 500, something like that. And anyway, that is a logarithm of almost a 2 or 3. And so before 2000, I start to handle the fullerenes, fullerene. Yeah, but anyway, so the molecular weight is around 1,000. That is the logarithm is just a 3. And then this is a big jump. So fullerene is the kind of really big organic molecule, and because the property and the structure, defined structure, is very similar to the organic molecule. But the carbon nanotube is normally a mixture, and it's a kind of various kind of lengths or the diameter or the alignment of the phenyl ring, and anyway, and also the molecular weight or the material is much bigger as compared to the fullerene. That is a kind of big jump. Anyway, so I continue to work with the nanocarbon material from fullerene to the carbon nanotube, and then so after moving from the Kyoto University to the Shiga University of Medical Science, I just started the biomedical application of the nanoparticle. And so at that time, of course, and I try to choose nanocarbon materials. But I'm afraid of some toxicity of the carbon nanotube. That's why I start to use the nanodiamond rather than the carbon nanotube. And so here I start to use the graphene around 2010. Then these are the nanocarbon material. Afterwards, I expand my variety of the nanomaterials from the carbon to for example, the boron or the iron or the molybdenum or the various kind of nanomaterial, nanoparticle or the nanosheet. Anyway, here, my research career is totally bottom up, from small to the large. organic chemistry to the material chemistry and the nanoscience. And so that this is our research concept. So that my research background or the academic background is organic chemistry. So the concept of our research is try organic chemistry to apply organic chemistry to nanomaterial. We assumed that so the nanomaterial is like the bigger organic molecule and try to apply some principle or the methodology of the organic chemistry to nanomaterials. One typical example is today's topics, host gas chemistry to the carbon nanotube, and so that the structure or the property-based separations. Anyway, so that we started from the fluorescence, fluorodome, and then moved to the one-dimensional, so the carbon nanotube, and the two-dimensional graphene, or the hexagonal boron nitride nanosheet, or the molybdenum disulfide, and some other 2D materials. And so that not only the nanodiamond as the 3D materials, but also the 10 boron enriched boron carbide, iron oxide nanoparticle. Anyway, so that we expand so that this field and to the not only the carbon from the carbon material to the various kind of nanomaterials. Okay, so this is so I will use the few slides to introduce different the subject of our research from the carbon nanotube separation, mainly the biomedical application of the nanoparticle, especially that this is focusing on the boron neutron capture therapy. So last night, when we moved from the Montreal to the here, Hamilton, and I talked with Alex, and I accidentally found that this university has a nuclear reactor, which might be a kind of generator of the neutron. And I asked him, and of course, they can order so that everybody can use the neutron as for his or her research, right? And here there is a nuclear reactor. Kyoto University also has a nuclear reactor, and we are collaborating with some medical doctors on the professors in the Komatsu campus, different campus from our campus, but anyway, it's a part of the Kyoto University, and we are collaborating and develop the new material for the BNCT. So anyway, I will show you some principle in the next slide. But anyway, here, the concept is a boron 10 packed nanoparticle for the BNCT. This is one typical example. Probably hexagonal boron nitride and 2D material. It's packed. When it's packed, and we can make it the kind of nanoparticle. Then we functionalize the surface of this nanoparticle with polyglycerol. PG stands for the polyglycerol. You may know that PEG, polyethylene glycol. It's a very typical, so that the hydrophilic polymer. So if you inject the vaccine, right, in the COVID, for the COVID, and it's also functionalized. So the surface was functionalized with PEG, polyethylene glycol. But so that we know, so this kind of the hard inorganic nanoparticle cannot be fully dispersed by the polyethylene glycol. Hydrophilicity is not enough, unfortunately. So after I moved from Kyoto University to the Shiga University of Medical Science, we start to find more appropriate hydrophilic polymers on the surface of the nanoparticle. And then we found that this polyglycerol, polyglycerol is more appropriate than the polyethylene glycol. Anyway, so that was published in 2011 in the Angewandte Chemie, and actually, so that afterwards, and we tried to apply this hydrophilic polymer to the various kind of the nanoparticle. And this is one example. Of course, after the functionalized with PG, it has enough dispersibility for the in vivo applications. And we use this for the boron neutron capture therapy and the BNCT. And so this is a sort of very general the method to exfoliate the 2D material. One is a graphite to graphene, and the other one is a molybdenum disulfide and the tungsten disulfide to the nanoseed. And we applied this methodology by use of the chlorine E6 as exfoliant. Chlorine E6 is a very good molecule for the photosensitizer, for the phototherapy, for cancer combating. Anyway, we can use it for the phototherapies, and we combined this phototherapeutic sensitizer, so the C6, chlorine E6, with boron nitride nanoseed for the BNCT. It's a bimodal therapy with a phototherapy and a neutron therapy, anyway. Okay, so this is a principle of the boron neutron capture therapy, and we need a boron 10 and also the neutron. And when they react, it generates alpha particle and the lithium nucleus. They can kill the cancer cell. And the characteristics of this distance of these two nanoparticles is within 10 micrometers, which is within the size of the one cells. That means that if we can selectively sense the boron 10 only in the cancer cells, if there is a healthy cell next to the cancer cell, and when we irradiate the neutron, so that only this boron 10 react to generate alpha particle and the lithium nucleus within the size of this cancer cell, we can kill selectively this cancer cell. But the next, so that the healthy cell should continue to survive anyway. That is a very selective cancer cell killing method for the BNCT. And of course, we need a neutron source. This is the neutron source here in the nuclear reactor. But we cannot use this nuclear reactor for the cancer patient. Anyway, it's very difficult. But anyway, technology has been developed, and we can utilize an accelerator-based neutron generator, which can be installed in the hospital. Actually, 6 hospitals or the institute in Japan already installed this kind of the neutron generator anyway. And the hospital in Japan already started clinically approved the cancer the treatment by use of this BNCT. And this the boron drug and steboronin or the boronophenylalanine BPA is the only approved boron drug. But anyway, this boron drug is not perfect, and there's a lot of problem. That's why we try to find the other better the boron drug. And then finally, that we reached to the nanomaterial, including the lot of B10. The one typical one is the boron carbide nanoparticle, B4C. The content is 80%. And we can enrich the boron 10 to the 100%. Natural abundance of B10 and the B11 is 1 to 4. That only the 20% is included in the naturally, anyway, B10. But anyway, we can intentionally enrich the B10 almost to the 100%. And then so I think the efficacy should be much improved. And so that our university, Kyoto University, has so the nuclear reactor. Of course, from the beginning, they are trying to improve the BNCT for the as a cancer therapy, and they have the 50 years so the history for the BNCT, and so that we collaborating with them and improved our nanomaterial based and boron 10 drug, and so the last year, just 1 year ago, and we established a private or the startup company named Radio Nanotherapeutics. Anyway, but anyway, so that at lunchtime, I talked with some professor in charge of the nuclear reactor, and yeah, it's a very fascinating and very impressive, and most probably, I will come back and yeah, talk again, and probably start the collaboration, most probably, and okay, so this is the result, one typical result of the BNCT for the mouse in vivo experimental result, and so there is a lot of control, and so the control is just implanted tumor mouse, and the injection control is just the material injection without any the neutron irradiation. Hot control is just neutron irradiation without injection of any materials. This BNCT is a combination injection of the boron drug and the irradiation of the neutron. So you could see that this standard conditions, and so we start the volume, so that the relative tumor volume from 1. And then, so control, it's getting larger and larger, and it's a logarithm scale, and getting larger and larger. But only the BNCT, so the cancer, the tumor volume decrease from 1 to almost 0. That means that almost all the mouse with totally fully treated, and the cured, and the efficacy is very good. And of course, no acute toxicity has been observed. And here, this is one index, in terms of the body weight, and it's gradually increased, and all I think that the groups of the cancer mice, and anyway, so that it's increasing gradually. And so that this is the typical pictures of each groups, and anyway, so the here BNCT group, and there's almost no that the tumor was disappeared, and at least much smaller as compared to the control group. And so this is the most fascinating the result by use of the 10 boron enriched boron carbide nanoparticles. Of course, on the surface was functional with a very good hydrophilic polymer, polyglycerol. So we call this material as RN501, and RN is our company name, Radio Nanotherapeutics. Then so the RN, and so that this drug was injected and to the cancer mice, and of course, so that we inject intravenously. That means that we inject from the tail vein, and then after the irradiation, and from the injection to the irradiation, so that we could have the 2 days. That means that it's gradually accumulated, slowly accumulated, and not so quickly removed. And anyway, then at the highest the concentration we observed after the 2 days, and then we start to irradiate the neutron, and then this is a result of the relative tumor volume, and from the 1, and anyway, so that at the control group, just the PBS phosphate buffer saline without any the drug, and so only the drug, only the neutron irradiation. These are the control group, and then the material injection and the neutron irradiations. So the efficacy is 80%. That means the 4 mice out of 5, so the totally cured. So the tumor was totally disappeared. So this is one kind of the cell line, cancer cell line, and in another cell line, and efficacy is not so good as the last one, so the previous one, but anyway, so the tumor growth is so the significantly suppressed, and anyway. Okay, so that these are some examples, typical example about so the boron neutron capture therapy. Okay, so we should change our brain and to the material science or the host gas chemistry for the separation of the carbon material. The first, yeah, so I would like to start from the fluorine because I was very much impressed by the fluor and so okay, so at the very beginning, this is the fluor dome, and also we can see that kind of fluorine in the park in Japan. So this is one example. Anyway, so this kind of the separation of the carbon materials by the host gas chemistry in a group has been started from this kind of host molecule named I think the calixarene. So here this is the 2D image. So we cannot see the 3D image, but anyway, you can guess if you run some organic chemistry, and there is a hydrogen bonding network here at the bottom, and there is a three the phenyl ring, and it has this cup-shaped shape, a cup shape anyway, and then some host molecule can be accepted inside this cap, molecular cap. Then I started to work with the fluorine, so before or around 2000. And unexpectedly, so this has the great affinity toward the C70 rather than the C60. Anyway, C70 has the complex, form the complex with this host molecule and the precipitate. So the fluorine is a kind of organic molecule, and here probably I use the toluene or the benzene as a solvent. It has a solubility, good solubility in the various kind of organic solvent. Then after complexation, it's formed a precipitate. That means that we can selectively obtain the C70 as the precipitate. We can easily separate them. This is very impressed to me. We can use the same or the similar strategy to separate the carbon nanotube, because in the very opposite way, so carbon nanotube doesn't dissolve any kind of solvent. And when it's formed a complex, if we can successfully dissolve in that solvent, of course we can easily separate. So that between the precipitate and the solution or the extract. Of course, at that time, if host molecule recognize some structure of the carbon nanotube, we can also separate the structure of the carbon nanotube at the same time. So this is our strategy to separate the carbon nanotube. Opposite way to the fluorine case. So there is a various kind of carbon nanotube, different diameter, different lengths, and a different alignment of the phenyl ring. And this play a very important role. This is a host molecule to recognize the structure of the carbon nanotube. This is the first generation we called diporphyrin nanotweezers. So here, so you can see the two porphyrin unit. Porphyrin itself has a very great affinity toward the surface of the carbon nanotube. Normally, commonly, so we use the word pi-pi interactions. Yeah. And we can change the spacer so that to tune the distance of the two porphyrin unit. Of course, we can tune the angles of that two porphyrin unit. Then we define the so that this cavity, and this cavity find the appropriate structure of the carbon nanotube. Of course, they form the very stable complex like this. And when so that it's formed the complex and disperse them in the organic solvent, so the color changed from this porphyrin color Lett to the blackish red color, including the carbon nanotube. Of course, so if that's a carbon nanotube, some carbon nanotube cannot form the stable complex, it cannot be dissolved or dispersed in the organic solvent. We can easily separate them by the centrifugation. And so after separation them, we can change the solvent to the washing process. In the washing process, then we can easily recover this host molecule and to leave the pristine carbon nanotube with a similar structures. This is our strategy to separate the carbon nanotube through the host gas chemistry. Okay, so I will introduce the typical structure of the host molecule from the first generation to the third generation. This is the first generation I've already shown you. So the porphyrin-based nanotweezers. And here we put the stereogenic center here at the periphery of the porphyrin unit. As I told you, the porphyrin itself has a great affinity towards the surface of the carbon nanotube. And then, if we put this stereogenic center, this R structure and the S structure can discriminate left-handed, right-handed structures of the carbon nanotube. This is the molecular design behind these stereogenic centers. So these are the publications. And so this is a second generation of the host molecule called porphyrin-based nanocalipers. And of course, the characteristics of this host molecule is a two porphyrin unit aligned in parallel. And it has a wider or the bigger or the deeper cavity as compared to the nanotweezers. We expect that the better, so that the more precise structure discrimination ability based on this nanocalipers. Of course, so that we can tune the distance between the two porphyrins. That's why we call this nanocalipers. And these are the publications. After 2017, actually, we didn't publish any paper for almost 5 years. And then 2022, so that we come back to this society, this third generation of the host molecule, we call the metal tethered nano bracket. It's kind of the nanocage to interlock the carbon nanotube. We connect these two nano bracket moiety through the metal coordination bonding. Of course, we can change the metals, copper and the cobalt, to tune the size of this nanocage. Of course, we change this so that the spacer unit, we change this distance to tune the size of this nanocage. Of course, we can change this ligand, dipyrin, to the phenanthroline to change the coordination moieties. Of course, we can change the metals. Anyway, the various kind of the size or the structure changing the part in this nanocage. And so that recently we published so that several papers based on this nanocage. This is also fascinating. And so that the day before yesterday, so the recent publication was accepted in the Chemistry and European Journal. And already, so that it is already so that online, so that you can see that so that this paper in online. And okay, so this is a brief introduction of the structure of the carbon nanotube. So there is two types of the carbon nanotube. One is chiral, the other one is achiral. Probably so that you may know what is the difference. Achiral structures, it can easily overlap the left-handed, right-handed structures. There is no difference between the left-handed, right-handed structure. But in the chiral carbon nanotube, you cannot overlap so that the left-handed or right-handed structure. That means the left, so anyway, so the two kind of, so that the structures. This is a chiral. And of course, on the chiral, so the carbon nanotube include so left-handed, right-handed structure at the 50 and 50% at the common, so the commercial carbon nanotube. And so this is the terminology of the NM structure of the single wall carbon nanotube. And anyway, there is a various kind of carbon nanotube called so the 6,5 and the 7,5 or the 8,6 and the various kind of carbon nanotube. So this is a terminology. And so that here, first of all, we put so that the graphene mapping, graphene map. So this is the origin 0, 0. And this is the 2 unit vectors to the A1 direction and the A2 direction. So if you want to compare the 5,3 single wall carbon nanotube, anyway, so that we can so define that these structures. First, go to the so that this zigzag directions in Japanese way. And 1, 2, 3, 4, 5. It is Japanese, okay? And this direction, we reach to the 5, 0, go 0 in Japanese. And anyway, in the A2 direction, 1, 2, 3, this is a go 3, 5, 3, the point. And if we lapped, so that the connect, that this 0, 0 to the 5, 3, go 3, in this way, this is a M structure. And the opposite way, this is so the P structure. MP stand for the left-handed, the right-handed structure. Anyway, we can so the prepare the M and the P 5,3 carbon nanotube. So every so the NM structure of the carbon nanotube is defined like this. Okay. So that here is so actual the results we obtained. So this is the first paper we published based on this, the carbon nanotube separation based on the host gas chemistry. And so here, as I told you, that we put the stereogenic center at the periphery of the porphyrin unit. And this successfully recognizes the left-handed and the right-handed structures. We independently applied this R structure and the S structure of the so that this nanotweezers. And so that we successfully separate and this left-handed and the right-handed structure of the carbon nanotube. And this is a synthesis. So we are organic chemists. That's why, so that we can design this kind of host molecule, and so that we can synthesize this kind of complex molecules. And finally, we use a Suzuki coupling reaction to connect these 3 components. So the spacer and the 2 porphyrin unit. And this is so the experimental procedure, how to separate, how to so the extract the carbon nanotube. We just mix this host molecule and the single wall carbon nanotube in methanol, bath sonication, and after some time we centrifuge and to separate the precipitate and the extract. And we separate the supernatant and then concentrate and wash out this host molecule by use of the pyridine or the THF, the different, the solvent, organic solvent, and dissolved this carbon nanotube in the presence of the surfactant STBS in the D2O, then measure the spectroscopies. So I will let you know that few typical examples. This is the mostly the important example and to define that we successfully separate the left-handed to right-handed structure of the carbon nanotube. This is a circular dichroism. As I told you that we independently extract the single carbon nanotube by use of the R structure nanotweezers and the S structures nanotweezers, and get the two the samples which is dispersed in the D2O in the presence of the achiral surfactant SDBS, and then measure the CD, and we can clearly see the symmetrical the CD spectrum from the R structure host molecule and the S structure host molecule. It clearly shows our extracted carbon nanotube is definitely the optically active. And this is the separation for the NM structure of the carbon nanotube. And before separation, we have at least three kind of the carbon nanotube is included. But after the separation, 7,5 and 8,4 was decreased in this absorption spectrum, and the relatively 6,5 was enriched. This clearly shows our host molecule also discriminates this NM structure or the size of the carbon nanotube. And this is a photoluminescence, the spectroscopies. Unfortunately, this cannot be seen, the metallic tube, but anyway, among the semiconducting carbon nanotube, 6,5 was clearly enriched. Okay, so this is a summary in this part, and anyway, our designed nano tweezers can discriminate only one specific animal structure with the R or the left-handed or right-handed, either left-handed or the right-handed structures. So this is a movie, and what is going on for the recognition of the carbon nanotube. I'm sorry, I don't know, that we can do this. No. It doesn't work. Sorry. Oh, okay. So anyway, this is a host molecule and the two porphyrin unit and the stereogenic center at the periphery. It's come close to the carbon nanotube with appropriate diameter, and it can also recognize a left-handed and a right-handed structure, and then that it's dispersed in the solution phase. Okay, this is that the computer generated, that the structure of the complex. So you can clearly see how deep carbon nanotube was captured in the cavity of the host molecule. So that in the case of this nanocaliper rather than the nanotweezers. And this is the nanocalipers synthesis procedure. Of course, we finally use the Suzuki coupling reactions to connect the two porphyrin unit to this kind of the spaces. And the characteristics of the nanocalipers is a very long spacer, 1.4 nanometer, and the parallel orientation of the two porphyrin unit, and the restricted conformation, especially that there is a single bond between the porphyrin and this spacer. This is somewhat restricted. And the recognition of the helicity by the stereogenic center at the periphery of the porphyrin unit. And the multi-point contact can be expected, not only the pi-pi stacking, pi-pi interaction, but also the CH-pi interaction at the spacer region. And this is so the typical examples and to compare the so the carbon nanotube before and after extractions. So this is a Rahman spectrum. So the Rahman shift is somewhat correlate with the diameter of the carbon nanotube. Larger Rahman shift means a smaller diameter. So the smaller Rahman shift is corresponding to the so relatively larger diameter of the carbon nanotube. And the Lett, so that this trace shows so that the before extraction, blue trace shows after the extraction. You can see the very big difference between them. So before extraction, this HIPCO tube include a relatively larger amount of the so that this smaller diameter, at least this excitation wavelength. So and after extraction, that larger component shift to the smaller. So that this is larger diameter. So that this is a smaller diameter. This smaller diameter component that shift to the larger diameter component as a majority. And so at the 633 nanometer excitation wavelengths, also the similar phenomena can be found. So that here, this is so the relatively smaller diameter, and it's shift to the larger diameter. In the case of the 488 nanometer excitation wavelengths, and this is so the little bit different. So the phenomena, so the here, so that there is a metallic tube and a semiconducting tube, and so metallic component is relatively slightly increased, and this is a region of the smaller diameter. Smaller diameter component didn't change so much. That means that we can expect this nanocaliper has a smaller diameter, larger diameter preference, and also the metallic tube preference rather than the semiconducting tube preference. So this is the absorption spectrum. It's may clearly found in this, so that the difference. So this is a metallic region, so that you can see the large upward shift in the metallic region. Also in the so that this semiconducting regions, we can clearly see the larger wavelength shift. Larger wavelength is corresponding to the larger diameter. Anyway, basically, this nanocaliper prefers a larger diameter, but at the same time, it's also prefer the metallic tube rather than the semiconducting tube. And this is the CD spectrum to confirm the recognition of the handedness of the carbon nanotube. So again, so that we can clearly see the symmetrical CD spectrum, which clearly shows so our nanocaliper can also recognize the handedness of the carbon nanotube. This is a summary. Actually, so that the selectivity is not so good as the last example, but anyway, this diameter preference is located around the 1.1 to the 1.2 nanometer, basically. But some smaller diameter metallic tube was also preferentially extracted. And so this is the multi-point recognition of this nanocaliper. As I told you, that there is a pi-pi interaction between the two porphin, and also this is anthracene in the spacer unit. And there is a CH-pi interaction between the surface of the carbon nanotube, and this is a CH bond here at the spacer. Anyway, so this multi-point the interactions more stabilize this carbon nanotube complex. Okay, so this is the final host molecule, like the nanocage to lock the carbon nanotube. of course, so that we synthesize, organically synthesize so that this molecule, and this is a bracket, and when we apply this kind of the metal ions to form so that this, so the cage structures, tetragonal copper nano brackets. And this is the crystal structures. So this is a kind of big, so the nanocage. So the weight is 1.83 nanometer and 1.44 nanometer. It's a relatively very big cage. Of course, it's enough space to accept the carbon nanotube. And here is the strategy to interlock or to separate the carbon nanotube. First, we mix the carbon nanotube with a nano bracket, and so that in the two propanol as a solvent and the sonicate, and so that this shallow nanocaliper also form the not so stable the complex, but when we add the copper, it's interlocked the carbon nanotube like this. And this is the one of the evidence to interlock the carbon nanotube. So we have a collaborator and a very good specialist of the TEM and the Hayashi sensei in Kyushu, Shinshu University. And this is an interlocking structure. So this carbon nanotube and this interlocked, and this, so that the distance is 1.73, and the interlocked carbon nanotube size is 0.89 nanometer. And this is a FM image, so supports this interlocking structures. So this is just so that the diameter of the pristine carbon nanotube, so 0.93 nanometer. And in this case, and probably we assume that this structure, not the interlocking, but this, so that the coordination bonding and form the complex. And so this, the size is a 1.56 nanometer. Here, when it's fully interlocked, so that this height, so that become the higher than 2 nanometer. Anyway, we think so that we can, so that see so this three kind of the complex or the uncomplex structure by the FM. And of course, so that it's from the interlocking structure, we expect the much better, so the size selective properties. And we found that the diameter range of the enriched carbon nanotube is from the 0.90 to the 0.92, only in the range of the 0.02 nanometer. And so here is another example of the host molecules. We just change, so anyway, so in this example, then this host molecule cannot recognize the left-handed and the right-handed structure. Then we apply that's the handedness discrimination ability toward this nano bracket or the nanocage. In this case, we use this kind of the very simple metal salt. This is a commercially available copper mandelate. And the copper mandelate actually form the supramolecular polymers like this. And of course, we can easily buy the R structure and the S structure of the copper mandelate. And when we apply the R structure or either the S structure of the copper mandelate, it can discriminate the left-handed and the right-handed structure of the carbon nanotube, form the complex like this. And when we apply this nano bracket afterwards of the metal salt, it can selectively form or selectively interlock the carbon nanotube where form the complex, where it form the complex with the copper mandelate. Finally, we can interlock we can disperse or extract selectively the interlocked carbon nanotube with the specific, the handedness. This is our strategy to separate the carbon nanotube with the left-handed and the right-handed structures. So this is again the TM structure of the interlocking, the carbon nanotube. And finally, so that we independently did this kind of the extraction by use of the R kappa mandrelate and S kappa mandrelate, and disperse and measure the CD once again, and so that we can obtain this symmetrical CD. That clearly shows that this kappa mandrelate or in combination with another bracket successfully recognize the left-handed and the right-handed structure of the carbon nanotube. And so this is the last example, and the quite recently published online in the chemistry European journals. And in this case, we changed this ligand from the dipyrine to the phenanthroline. So this phenanthroline is a somewhat the wider region of the pi system, which can have the more stable complex with the carbon nanotube. And in this case, we change the metals from the palladium to the cobalt, and we can tune the preference towards the diameter of the carbon nanotube. When we apply this palladium to this carbon nanotube extractions, the smaller diameter range from the 0.84 to the 0.92 nanometer range. And when we apply the cobalt instead of the palladium, we successfully separate the larger diameter of the carbon nanotube from the 0.97 to the 1.05. Anyway, we simply change the kind of metals, but we can selectively extract the different size of the carbon nanotube. This is very fascinating. This was my student was presented this result at the Chem Tube, and she got a prize, and then we got the invitation from the Chemistry European Journal, and successfully it was published. Anyway, in this case, we didn't say that this is an interlocking structure, a kind of wrapping with a supramolecular polymers like this. In this case, changing the ligand, changing the structure of the host molecule on the surface of the carbon nanotube. Anyway, in this case, supramolecular polymer wrap the carbon nanotube like this. Okay, this is a very simple summary. We successfully applied the host gas chemistry to separate the carbon nanotube according to the handedness, the diameter, or the metallicity-based separations. And this is a very beautiful, fascinating image in the spring of the Kyoto city. And so have you ever been to Kyoto, or have you ever been to Japan? Oh, the Kyoto city, how about the Kyoto? Oh, okay, probably so that you enjoy a lot, right? Unfortunately. Okay, so you have to carefully choose the season, and this is spring, and the end of March or the beginning of April, the best season. But anyway, the most cloudy, of course. Yeah, so if you have a chance, please visit Kyoto City. Okay, thank you very much for your kind attention.
I'm curious. So on the one slide you showed the users that had a very high concentration of phthalates. I'm just curious. You still had some semiconducting. If you look at the semiconducting
So anyway, it's a little bit difficult for us to identify or to clearly see that which kind of the factor is more influential and but anyway, for the so that we carefully see the various kind of information and the basically so that it's preferred so that this kind of diameter range, but the exceptionally so that it's formed some stable complex with a metallic tube rather than the semiconducting tube. I cannot show you the detail, but anyway, so I think that our conclusion is correct.
On the same note, did you look at different solvents for those dispersions? If solvent will impact whether you're dispersing metallic or
Yeah, that is a good question. So actually, so the solvent play a very important role for the separation. At least so the how much amount of the carbon nanotube is extracted. If we apply the very good solvent, which has a very good extracting ability, and so the selectivity should decrease. And if the very small amount or the no carbon nanotube is extracted, and it's nothing or no meaning, right? And we carefully choose appropriate so that the solvent. And I already published that so that one or two papers about the screening of the solvent, and we always find that methanol is the best solvent. Methanol. We always use the methanol for the extraction solvent. Yeah, and it shows a very good the selectivity always. Yeah, thank you very much.